JFB 103. This is a special colloquium by Dr. George Lowe, who is a legendary alpine climber and highly skilled scientist and engineer, who will tell us about both climbing and physics, which sounds kind of awesome. Second announcement is that we have dinner plans to go to the Red Iguana after Jason's talk, so if you'd like to join for dinner, please let me know, and I will do my best. And finally, some of you may recognize Jason from the teleconference machine in JFB 210, but we're very happy to have him here in person this week. Jason got his bachelor's degree from Caltech, his PhD from Stanford, and spent time at San Diego, Michigan, Texas A&M, and Irvine before landing his main gig as an associate professor at the University of Hawaii. So Jason is going to tell us about WIMPs. So let's welcome Jason.
Thank you very much. So I'm going to talk about WIMPs, status, and prospects. And kind of the outline of my talk is I'm going to start out by sort of motivating dark matter and why we care about it, introduce sort of what we talk about when we're thinking about weakly interacting massive particles, or WIMPs, in particular what our favorite kind of WIMP candidates are. And then go on to talk about what the most recent data has been telling us about dark matter, in particular the role of our assumptions about WIMPs in terms of how we analyze dark matter, or how we analyze the data from dark matter experiments. And then I'm going to go on to talk about what are some of the options for how we can reconcile our theoretical models with what we're finding from our experiments, in particular what happens if dark matter is a little bit more complicated than some of our initial favorite WIMP models. And finally, I'll discuss a little bit of the outlook for sort of what we might learn from upcoming data. And so to start off, when we talk about motivating dark matter, there's a lot of evidence from a wide variety of length scales, from the scales of galaxies all the way to the size of the CMB, which provides some of our motivation for thinking about dark matter. But I'm going to focus just on the evidence we get from the rotation curves of galaxies, basically because not only does that provide some of our motivation for believing in WIMPs, or I should say dark matter, but also provides some of the, what we think about in terms of the properties of dark matter and how that helps us interpret the data we get from some of these direct detection experiments. And so when we think about how you look at rotation curves of galaxies and how that provides us evidence for dark matter, it's in many ways similar to the way that great physicist Obi-Wan Kenobi finds evidence for the Camino star system from the Jedi star maps. And so if you remember the movie, what he's looking for the Camino star system, but he can't see it because it's been erased from the star map. But the thing you couldn't erase is the effect of Camino's gravity on all the other stars in the area. And so by analyzing the motion of the other stars, he can infer that there has to be some other gravitational force beyond those from the stars he can see. And from that, he can infer where Camino had to be. And so the way we kind of find evidence for dark matter from galactic rotation curves is basically the same idea. It's to kind of relate the centripetal acceleration, which is keeping these stars in orbit around the galaxy, with the gravitational acceleration, which is generated by the mass enclosed within any particular radius. And so the idea is that if all of the matter in the galaxy really were where it appears to be, where the visible stuff is in the bright galactic center and the galactic disk, then once you get beyond that, this enclosed mass should basically become constant. And then your velocity should fall off, like it does here in this sort of Wikipedia graph. But what we actually observe in spiral galaxies is that these rotation curves tend to flatten out and essentially become constant. And so you can see from here that if this velocity is becoming constant, it's implying that this enclosed mass is actually growing linearly with the distance. And so what that's kind of telling us is that the total mass is much larger than this visible mass which we're seeing. And so we can try to interpret this in terms of a new particle, kind of particle dark matter. So the idea that there's some new stable particle which is making up all of this extra matter. And so if we assume that this enclosed mass has this linear relation and we parameterize it with just some scaling coefficient alpha, then we can use some techniques like the virial theorem, for example, to try to figure out what the average velocity of dark matter should be. And it turns out it just goes like alpha times g Newton up to a couple of factors. And so this whole behavior of a linearly growing mass and this constant velocity distribution, or average velocity, roughly fits in with a model of dark matter as just an isothermal sphere. So basically an ideal gas at fixed temperature, which is exhibiting spherical symmetry. And so kind of our input for this entire analysis and determining these coefficients just comes from this velocity here, this rotational velocity. And for a galaxy like the Milky Way, our measurements are that that's roughly about 220 kilometers per second. And so by plugging that back in and then determining these coefficients, we can feed through and not only determine what the dark matter density should be, but also what the velocity distribution is in the neighborhood of the solar system. And of course, there are uncertainties in this. One of the biggest sources of uncertainty is the fact that it's hard to measure the properties of a galaxy when you're inside the galaxy. But even up to those uncertainties, it kind of gives us a handle on some of the properties that particle dark matter could have. And so if we think about what are the properties we think of dark matter as having, I've kind of tried to break them up into three groups: things we think we know, things we assume, and things we just guess. And so among the things we know, one of them, for example, is that dark matter is a particle. Now, of course, this doesn't actually have to be the solution. A lot of people have thought about modifying Newtonian dynamics or some modified version of gravity as a possible solution for dark matter. Primordial black holes are another possibility. But I'm going to focus on particle dark matter largely because, in many ways, this is the most sort of popular model among what people think of. And one reason, and perhaps is a very subjective one, is the idea that because we have evidence for dark matter which comes from a wide variety of sources and a wide variety of distance scales, particle dark matter becomes one simple way of kind of explaining a large part of that evidence. And so largely for that reason, I'll just mostly focus on this. And we also believe, or we think we know, that it's dark. So basically it doesn't interact very strongly with light. And that it's very long-lived. So it's either exactly stable or its lifetime is much longer than the age of the universe. We also think we know that it's about 80% of all matter in the universe. And the density near Earth is about 0.3 GeV per centimeter cubed. Now, one of the things we assume, for example, is this velocity distribution. We assume it's this kind of thermal Maxwell-Boltzmann distribution. So roughly this form here, where the velocity scale, which kind of controls this distribution, as we saw, in about the 200 to 300 kilometers per second range. So it's very non-relativistic. You can kind of compare that for scale with, say, the escape velocity from the galaxy at our position in the galaxy. Now, I say this is one of the things we assume because we actually think this probably isn't true. That this isothermal sphere model is probably not correct. And basically it's because people who do large n-body simulations of how dark matter ought to behave find that when you look at how galaxies form, that it probably really doesn't exactly thermalize and form some isothermal sphere, that you get deviations from that. And so, although we kind of think that this velocity distribution probably shouldn't be exactly of this form, this is a somewhat reasonable approximation to it, and it becomes a nice benchmark which everyone can use, because once you depart from this, you're really not sure what the deviations from this are. So this becomes kind of a nice benchmark which people often use. And lastly, in terms of things which we guess at, what I would say is kind of the guess which most people make is that dark matter is a thermal WIMP, and in particular, the lightest neutralino of the minimal supersymmetric standard model. And I'll try to sort of describe in more detail what all is implied by this and what this means, but kind of the properties we get out of this is that our dark matter's mass is roughly in the 10 to 1,000 GeV range, usually somewhere in the middle of this. That the relative density which we would compute just by doing thermodynamic calculations approximately should match what we observe. That it's a Majorana fermion, so it's a spin 1/2 particle, which is its own antiparticle. But all of these guesses are really only true, if this guess here is correct. And so, we can kind of think about why, we make these kind of guesses, why this idea of a thermal WIMP, and what that means, and why that becomes our leading guess for what dark matter is. And so the idea is something which is often called the WIMP miracle. And the basic idea is to think about how the universe was, much earlier on when the universe was smaller and it was much hotter. And the idea there is that matter was basically in thermal equilibrium. So dark matter particles would be annihilating to create light, relativistic standard model particles. Standard model particles are annihilating to create dark matter particles. But what happens is that as the universe cools and expands, eventually dark matter decouples from equilibrium, basically because of the expansion of the universe. So as the particles expand apart, the dark matter particles can't find each other to annihilate anymore. And so when that happens, this annihilation process freezes out, and dark matter essentially decouples from this equilibrium number density and just scales out with the expansion of the universe. And so the idea is that to figure out what that density was, all we really need to know is the annihilation cross-section. Because to find out when this freeze-out occurs, we just need to relate the expansion rate, which comes from the Hubble expansion parameter at that time, to the dark matter annihilation rate, which comes from the dark matter number density times this annihilation cross-section. And so to get the Rayleigh density which we observe, or what, the density which we infer for dark matter from astronomical observations, we would need this annihilation cross-section to be about a picobar. And so if we think of it as something which should be about a picobar, we can ask, how should that scale with the parameters of particle physics? So for example, if the interactions which are mediating dark matter decay scale with a coupling which I'll just call G, then this annihilation cross-section should scale like G to the 4th, basically by power counting the number of interactions in an annihilation cross-section. And if the mass of the dark matter is something I'll call M, and that's the characteristic energy of the annihilation process, then this annihilation cross-section should scale as M to the -2, basically from dimensional analysis. Because it's a cross-section, it goes like an area, so that's energy to the -2. And this is essentially the ruler in the problem, the thing setting the energy scale. And so, what the WIMP miracle is the remarkable fact that if I have a stable particle whose coupling and mass are characteristic of the electroweak theory. So I just take the standard, weak coupling constant, about 0.6, the mass of the electroweak scale, the mass of, approximately the W's and Z bosons, which is about 100 GeV. I just put them in here, and of course, there are a few factors of 2 pi around, but roughly this is the formula you put it into, and you end up getting about a picobar. So a stable particle which is characteristic of this electroweak theory naturally has about the right Rayleigh density to explain our observations. And this, in many ways, people kind of said is kind of this miraculous coincidence in the sense that this number could have been 6 orders of magnitude off. The fact that it gets so close to what you observe, and that with realistic models, which are not terribly strange, you actually get the Rayleigh density right, is what caused a lot of people to think that this is a really good guess for what dark matter could be. Now, when people talk about dark matter, they often think about this as something which comes out of supersymmetry. But you'll notice I've not mentioned anything about supersymmetry yet. This is just talking about particles which are characteristic of electroweak physics. Where supersymmetry enters this is that supersymmetry is a nice model for what happens at the electroweak scale, what generates electroweak physics. And in particular, it becomes a nice implementation for this idea, a way of getting a stable particle which has these properties. And so kind of where dark matter comes into this picture is when we think about how we would get a stable particle. And so usually when we think about why particles are stable, it's often because it's the lightest particle which has some conserved charge. So basically you can't decay to anything which is lighter while still conserving that charge. So for example, that's why we would say electrons are stable, because it's the lightest particle which is charged under electromagnetism. And so supersymmetry is kind of a well-studied model of new physics. And kind of the basic central feature of it is that every particle is going to have a superpartner, sort of a partner particle which has all the same quantum numbers except the spin, which differs by 1/2. And that was introduced to essentially address a bunch of problems of theoretical physics. So for example, the hierarchy problem, which is essentially the question of why the scale of electric symmetry breaking is so much lower than the scale of, say, the Planck scale. It also addressed issues like in understanding grand unification. But one of the nice features of supersymmetry is that this lightest supersymmetric particle, this lightest superpartner, which is something that's called the LSP, is often a good candidate for dark matter. Basically because it's a neutral particle, which in many of these models ends up being a neutral fermion, which is often called a neutralino, which naturally has a weak scale coupling and a weak scale mass, and which ends up being stabilized by a symmetry called dark parity. So this kind of becomes a natural dark matter candidate to come out of this framework. Now you'll notice I put a little c here in front of MSSM. So the idea of the MSSM is that it's the minimal supersymmetric standard model, kind of the minimal theory you can write, which has all the particles and symmetries you need to get supersymmetry. But when you do that, you get like a huge number of parameters for all the new particles you've added. This theory has well over 100 parameters. So it's a very difficult thing to manage. And so what people have often done in looking at this is to make a bunch of well-motivated assumptions on what are the correlations between these different parameters, how they're constrained. And once you make some of these well-motivated assumptions, you end up with a model which only has maybe 4 or 5 parameters. And there's some variations in how people make those constraints, but they have a lot of very generic features in common. And this CMSSM and the lightest supersymmetric particle in that framework really becomes kind of the favorite WIMP candidate, the nice, elegant, simple one which everyone loves to study. And the way I kind of phrase it is, it's like kind of like the candidate under the lamppost, the one which everyone gets to look at. But kind of one of the important things for looking at dark matter searches is that for many of these WIMP searches, they implicitly assume this candidate and all of the assumptions which went into that. But of course, as Sherlock Holmes would say, it's a huge mistake to theorize before one has data. On the other hand, I'm a theorist, so that's kind of my job. So, yeah. But that being said, now that we're getting data from experiments, it kind of makes sense to sort of turn it around and see what data tells us about some of these assumptions we've already put into here. And so that's kind of, my next topic, which is just to talk about what data is telling us and what role those assumptions of the CMSSM have played in understanding that analysis. And so people search for dark matter using a wide variety of experiments from all over the world, from Italy to this prototype detector being made at University of Hawaii, to experiments in Antarctica, all the way to experiments in space at the International Space Station, and everywhere else in between. In fact, these 4 experiments are experiments which people work on at University of Hawaii. But of all these very different experiments, you can roughly kind of sort of break them down into almost like 3 types of categories. And we can kind of see them from this kind of a diagram here. And so if I follow this diagram upwards, we get direct detection, which is basically the idea of having a dark matter particle scatter off a standard model particle, like a nucleus. And what you try to measure is the recoil energy of this bump in the night. If we take the same diagram and try to follow it to the right, we get the idea of indirect detection. Which is basically the idea of dark matter annihilating somewhere in the cosmos, somewhere where there's a large dark matter density, and producing standard model particles. And then you just want some kind of an observatory or telescope to see these standard model particles as cosmic rays. Then if you follow the same diagram back to the left, you kind of get the sort of the reverse process, which is standard model particles like protons being collided at the LHC, and then producing dark matter. Now, since the dark matter is very weakly interacting, or at least it is in these WIMP models, it's going to pass right through the detector. So sort of what you'll see is the missing energy, the missed momentum, which you should have seen in that direction, but didn't. And so we kind of want to sum up sort of what's the status of all this recent data. The first thing is there's no confirmed signals of anything. But there's some hints. I just kind of summarize some of the sort of most prominent ones. So for example, there's a positron fraction rise, which people have, a rise in the positron fraction, which people see when looking at the electron cosmic ray data. And this has been seen in experiments like Pamela, for example, and most recently in the AMS experiment. And so then there's also, for example, hints for example, the possibility of low mass dark matter, which people have seen at some direct detection experiments. Then there are also a few hints looking at photons from the galactic center. So there's been an excess of order 10 GeV photons, which people have seen from the galactic center. And there's also been sort of a different hint, which is a monoenergetic signal of photons. So a bunch of photons at about the same energy, about 130 GeV, also coming from the galactic center. But kind of one thing to emphasize is that all of these hints are challenged in some way. So some of them are contradicted by other experiments which aren't seeing anything when you would imagine that they should see something, given what this experiment's seeing hints have seen. In other cases, it's just a matter of statistics. You're seeing some kind of a signal, but it's not, the statistical significance isn't really high. One finds very quickly in this field that publishable, people will make a big deal about signals, which in other fields you wouldn't even write a paper about yet. And then, another big issue is just the systematic uncertainties in all of these things, which amount to basically uncertainties not only in sort of your understanding of the background, but just in your understanding of the experiment itself. Because these are very hard experiments to run. And so there are challenges to all of these experiments in some way. Sort of on the other side, though, we do get from these experiments some very tight bounds on what dark matter could be. And sort of from the direct detection side, the most recent and tightest bounds come from an experiment called the LUX experiment in South Dakota. From looking at indirect detection and photons, some of the tightest and most solid bounds come from looking at dwarf spheroidal galaxies, looking for photons. And then there are bounds from LHC searches. And I was just going to kind of go through these one by one to see what these things are really telling us and how that reflects on our assumptions about dark matter. So I was going to start with direct detection. And I've always kind of found it interesting that this is this field where all these experiments are built and so many experimentalists work on this. But this field was actually originally proposed by 2 string theorists, Mark Goodman and Edward Witten. But now kind of everyone has been working on this, and the basic idea is to look for dark matter scattering against the nucleus, and then trying to measure that recoil energy. Now, that scattering process is largely coherent. So basically, at that kind of energy range, we're not breaking the nucleus apart. The nucleus is just sort of scattering as a whole. And if we kind of think about the nucleons which are making up this nucleus, and what are the properties of them which are relevant for scattering, for the most part, there are basically two things which are important, which is basically what's the type? Is it a proton or a neutron? Or what's the spin? Is it spin up or spin down? And so that kind of lets us roughly separate the scattering process into two classes. They're sort of spin-independent scattering, where basically the only thing you're coupling to is the number of nucleons. And kind of the classic example of this is electromagnetic scattering, where basically all you care about are the total number of protons, which each couple with strength 1, and the total number of neutrons, which each couple with strength 0. So essentially you don't care about the neutrons. The other kind of example is where you're coupling to the nucleon spin. And so you can see that if you're just coupling to the nucleon number, your cross-section essentially scales as that number squared. Whereas if you're coupling to the total spin, it's essentially coupling as j squared. But you can kind of see that this cross-section will tend to be a lot larger than that cross-section, basically just because here everything's adding up. It's almost like constructive interference. Where here, typically your spin's anti-aligned, and you're getting as much destructive interference as you can. So basically you expect these kind of cross-sections to be larger than these kind of cross-sections. And kind of the thing you end up measuring from here is the recoil energy of this kind of a nucleus. And we can kind of think about that just from two-body kinematics. And to get like a rough idea of what the scale of this is, the maximum recoil energy you can get is basically if you have just back-to-back scattering, in center of mass frame. And so you can kind of figure out what that maximum recoil energy should be, and it just comes from this formula here, where this is the reduced mass squared, this is the mass of your target, and this velocity squared is that relative velocity. And we already got a handle on that. It's sort of this 200 kilometers per second or so, which we got from the velocity distribution. So kind of plugging this in, you expect these recoil energies to actually be fairly small, about 100 keV or so. And so people have a variety of bounds which they get. And unfortunately, I guess it might be a little bit hard to see these in the back. These are basically a series of bounds from the innumerable experiments people have looking for that. This is dark matter, this is spin-independent scattering, and spin-dependent scattering, from a variety of different experiments, all made with different targets, which are looking for dark matter scattering off a nucleus. And basically ruling out everything above these lines, where on the x-axis is the mass of your dark matter, and on the y-axis is the cross-section for dark matter to scatter off a single nucleon. And so one thing I just want to quickly mention is that what all of these bounds are assuming, kind of what's gone, part of the assumptions which have gone into this analysis, for example, is that scattering is an elastic scattering process. That scattering is a contact interaction. So essentially, the force-mediating scattering is a very short-range force compared to the momentum transfer. And as we saw, these momentum transfers are already fairly small because these recoil energies are fairly small. And another assumption is that, for example, you have the same coupling to protons and neutrons. And I kind of parameterize that by numbers Fn and Fp. Now, where that comes in is that, as you can see, what each of these detectors would be measuring is the cross-section for dark matter to scatter off whatever nucleus is in the detector, whether it's germanium or silicon or xenon or sodium or whatever. And so since these are all different targets, all those cross-sections are going to be different. So comparing them to each other doesn't really tell you anything. So instead what you'd like to do is to pick one target which can be sort of your standard. And from your cross-section, the bound on your cross-section against any target, just find a way to rescale and infer what your bound would have been off this fixed target, which is usually a single proton. And the idea is the only way to do that is to make an assumption about the relative coupling strength between protons and neutrons. And usually you just assume it's the same. So that way, these cross-sections have a simple scaling with the number of nucleons. You scale that out, and you can find a scattering cross-section off a single nucleon. And then you can write all the experiments with bounds on the same axis, and you can compare their results to each other. Now, these assumptions here are all true for the CMSSM, but generically they're not true at all, even for MSSM models, let alone for non-MSSM WIMP models. Now, there are just a couple of features on this I'd just like to briefly mention. So again, I'm not sure if you can kind of see the axes here, but one thing you might notice is that these bounds on spin-independent scattering tend to be at much higher cross-sections than on spin-dependent scattering. And again, you can kind of see why. Because you had all this constructive interference here, you tend to have very large cross-sections here. So spin-independent scattering has essentially is very sensitive. For spin-dependent scattering, since you have a lot of destructive interference, these results tend to not be very sensitive. So kind of this is sort of the money plot. This is what everyone kind of focuses on in terms of how you'd want to find dark matter. It's a spin-independent scattering. Another thing you'll notice is that these sensitivities all get better as you go to lower and lower mass. But then suddenly they all get really bad at some point. And when it gets bad, is different for different targets. And again, one can kind of understand that just from this expression here for the recoil energy. So you can see it. This is the maximum recoil energy. As I make the mass of my target smaller and smaller, the mass of my dark matter smaller and smaller, the reduced mass of my dark matter nucleus system, that also gets smaller. So this maximum recoil energy is getting smaller and smaller. But all of these experiments kind of have a minimum recoil energy, kind of a threshold. The idea being that for recoils which are below that energy, you just can't distinguish it from background. So if you've got a threshold here, and you keep moving your maximum down, essentially you're squeezing all your events below the threshold, and you're just not seeing anything. And when that happens, that's when all these experiments start losing sensitivity down here. So kind of how these experiments function depends a lot on where the mass of your dark matter is. So that's kind of the story of how direct detection has been working. I was going to kind of shift gears now and kind of talk a little about what indirect detection has been telling us. And here, there's a lot of indirect detection experiments, but I kind of want to pick two different types as kind of counterpoints to each other. So when people look for photons from dwarf spheroidal galaxies, in some ways that's notable as providing one of the most solid bounds on dark matter annihilation. So there I think about more in terms of bounding something. And the basic reason is because these dwarf spheroidal galaxies tend to be dominated by dark matter. So what that means is that there's very little astrophysical background there. There aren't a lot of stars, pulsars, a lot of things which could be producing photons which you don't understand but which aren't dark matter. That stuff is sort of, that source of uncertainty is at its minimum in these dwarf spheroidal galaxies. And so here, for example, is a set of bounds on the dark matter annihilation cross-section as a function of mass. If you assume dark matter is annihilating to, for example, either BB bars, so bottom quark, anti-bottom quark, or tau lepton, anti-tau lepton. And the idea is that if dark matter annihilates to either of those particles decay, produce a bunch of photons. So if I know the annihilation cross-section and I go through the spectrum, so the bound on how many photons I see from these dwarf spheroidals lets me put a bound on what this annihilation cross-section should be. And I'll just mention that one can often get comparable bounds on these annihilation cross-sections by looking at something which isn't an indirect detection experiment at all, but is actually just looking at distortions of the cosmic microwave background, which can be caused by the photons produced from dark matter annihilation. But kind of the counterpoint to this kind of search at dwarf spheroidals is looking for photons from the galactic center, because that's a place where you expect to get the largest signal, the largest number of photons from dark matter. Basically because that's where you expect to have a large number density of dark matter. You expect to have a lot of dark matter at the galactic center. In fact, much more than these dwarf spheroidals. But kind of the downside to that is that's also where there's a lot of stuff, unlike dwarf spheroidals. Everything's in the galactic center. And it's really hard to disentangle any kind of signal you can see from there, any of these hints we were talking about earlier, from all the crazy astrophysics which could be going on there. So although this becomes a great place to look if you want to see something, it's not as great a place to look if you want to put a... I'm sorry, you had a question?
Oh, so can you say one more thing about the CMB bounds? What's the epoch for the dark matter annihilation that leads to those?
Oh, this is dark matter at around... so it's actually at the time of recombination all the way to much earlier than that. So I think it actually... When dark matter annihilation becomes important for that is when the universe is, I think, like 10 to the 6 seconds old. So actually quite a bit earlier than recombination. And the idea is just that for dark matter with that kind, let's say, which is being annihilated to photons of that era, you end up producing a bunch of photons which can distort the CMB because they don't have enough time to thermalize.
That was maybe my next question, is I don't understand why it wouldn't re-thermalize.
To be honest, the details of that I'm not entirely sure, but I think the problem is that the energy can rethermalize, but the number of particles doesn't. So one way to look at it, is there a piece of chalk I can use? Yeah. So the idea is that if you just have a Compton scattering process, for example, so something like this, then you can use that to sort of rethermalize the energy, but it's not going to change the number of photons. To do that, you need one of these processes where you get another photon off. And those processes tend to decouple a little bit earlier. So you kind of get a thermal spectrum, but with the chemical potential. And you get tight bounds on that from the CMB. So that's the kind of thing which puts bounds on it much earlier than the era of recombination where you might expect it. Although, to be honest, the details of that I'd have to think a little bit harder about. Is that answer?
I don't completely understand either, but it's okay.
Maybe we can talk about it
Yeah.
later. Yeah. Okay, yeah. So this is kind of a counterpoint to that. But one thing we can kind of see from all of these kind of studies is that where we expect to get the best sort of information from indirect detection is when your dark matter particle has a low mass. And the basic idea is because sort of one way to look at that, what astrophysics tends to get a handle on is sort of the mass of some kind of an astrophysical body, like a dwarf galaxy or something like that. So if you can get a handle on the mass enclosed in some radius, but the particle mass is very small, that means the number density of particles has to be very large. And your annihilation cross-section goes like your number density squared, so that increases the amount of signal you end up getting. And so that, for example, is why all these bounds are getting better and better as you get a lower and lower mass. Now, this dotted line here is that 1 picobar line, which is where you expected WIMP annihilation to be. So one thing you might do is kind of look at this and say, well, all these models here, doesn't that mean this WIMP miracle gets ruled out for these models? At least the dark matter is annihilating to B quarks or tau leptons. And it turns out that's not the case. In fact, indirect detection doesn't have to see anything. And the basic reason is because dark matter could annihilate particles which are initially in a P wave state, so some state with angular momentum. And if that's the case, then that means that your annihilation cross-section is proportional to velocity squared. Now, at the time when this annihilation process was freezing out in the early universe, and your cross-section needs to be 1 picobar, V squared ends up being about 0.1. So that's essentially a 10% suppression on your cross-section. So that is significant, and that can have an effect on making this WIMP miracle tougher. But there's some play, in those parameters, in that range of masses. So that's something which people can overcome. But nowadays, V squared will be about 10 to the minus 6. So that cross-section gets really suppressed. So if that WIMP miracle is working at freeze-out, you have such a 10 to the 5 suppression on what your annihilation rate would be now. And it becomes a lot harder to see anything. So you might not see anything from indirect detection. It depends a little bit on the model. Now, going on to looking at what the LHC tells us, in some sense, there are 2 LHC strategies, which are kind of complementary to each other. Kind of the first kind of classic strategy is basically for the LHC to produce some heavy particles which are coupled to QCD, so essentially coupled to the strong force, but which are also charged under the same symmetry, which is stabilizing the dark matter. And the idea is that once you produce them, because of charge conservation, they have to decay to the lightest particle, which also has the same charge, and that's the dark matter. So you end up producing dark matter, which just looks like missing momentum in your detector, plus a bunch of jets. And so, kind of the nice thing about this is that this is the kind of thing the LHC excels at. Because producing things with a strong force, that's what the LHC was built for. That's what it's really good at. It's essentially a QCD machine. It produces everything with a strong force. And then there's the case the dark matter are just forced by charge conservation. So you know that as long as you have enough energy, you'll produce a ton of these particles. And this is kind of what a bunch of all these SUSY searches are all about. And so what I've put here is a figure from the Atlas experiment about different searches and different channels for a bunch of SUSY particles. And you probably can't read anything here, and that's kind of the point. There are a whole bunch of searches, and the only thing we kind of need to know from that is that none of them see anything yet. But kind of the interesting point is that these are all about searches for the heavy particles. They're not really dark matter searches. These are all about ways about producing these heavy particles. And then the stuff which it decays to is just some missing momentum at the end. So what you really learn about is the heavy stuff. And it's only very indirectly that you learn about the existence of this dark matter stuff, which is just the missing momentum at the end of the chain. Kind of the complementary way of looking at it are these things which are called monojet or monophoton searches, which is basically where you produce dark matter directly through that same kind of contact interaction I showed in that earlier diagram, which was also mediating direct detection and indirect detection. And so the idea is that your proton and your 2 protons are annihilating to produce some dark matter pair. And then you're also getting some jets or photons which are also emitted just so we have something to recoil against. So you see something in the detector. And the nice thing is that because this is coming from that same contact interaction, which is directly relating sort of dark matter to standard model particles, you can kind of relate your event rate here to what you see at direct detection experiments, and kind of relate these bounds to each other. But sort of the flip side of that is that this is only true if that assumption of this being a short-range force, a contact interaction, is valid. And I don't mean now just valid at the energies of direct detection, which are just 100 keV. It's easy to make that a contact interaction. but now to make this a short-range force, even at the energy scales of the LHC, which are very high energy, so very short distances. So it's only in that limited context in which you can really make this connection. And once you go beyond that, it now starts to depend on the details of what's going on in the short-range force, essentially on the same kind of heavy physics, which we're probing with this other strategy as well. And so I kind of want to do, instead of going into more detail about how these searches are done, is trying to focus on what we learned as kind of the upshot of these searches for what our favorite WIMP candidate was, this CMSSM. And the basic idea of what we're finding is that essentially it's hard for the CMSSM to match data. Basically because essentially what the LHC requires is that the superpartners of the gluon, that partner is called the gluino, and of the up and down quarks, and those superpartners are called squarks, those basically have to be very heavy. And in fact, the mass of the Higgs also tells us that the partner of the top quark is probably going to be very heavy. Now, in the CMSSM, what that basically implies is that all the superpartners have to be heavy. And what that ends up doing is suppressing the annihilation cross-section, because as we saw earlier, that cross-section scales as mass to the -2. So if I'm making all the masses of these new partners heavy, this characteristic scale heavier and heavier, I'm making that cross-section smaller and smaller. And it makes it harder for this WIMP miracle to work. Now, it still can. There are still things you can do to kind of increase that cross-section a bit. But now it's not easy anymore. You've got to work out. In addition, what we find in the CMSSM is that spin-independent scattering basically comes from exchanging a Higgs boson. And we'll see why that's true a little bit later. That kind of leads to two things. One is that the rate for this Higgs exchange process could be very small. So we might not see anything at a direct detection experiment. But the current limits we already see from LUX tell it has to be pretty small. And that actually ends up making it tougher for the WIMP miracle to work, because basically some of the ways we can use to get around this problem and to ramp up that annihilation cross-section end up implying a coupling to the Higgs boson, which would get ruled out by the spin-independent scatter. So they kind of both work together to make this CMSSM harder to realize. Now, indirect detection hasn't seen anything definite, but there's no reason it has to for the CMSSM, because you could just have this P-wave annihilation, in which case you're not going to see anything in the current element. And how we try to correlate direct detection bounds, even with each other, let alone with indirect detection and with collider experiments, depends a lot on the details of these assumptions. So in some sense, the upshot of this is that even though the CMSSM is hard to match with data, our favorite WIMP candidate, even just eliminating the C and going back to the MSSM makes the whole picture work fine again. And not let alone looking at non-MSSM WIMP. And so kind of my goal for the next part is basically to talk about what are those options. So how can we make dark matter just a little bit more complicated than the CMSSM and sort of resolve these data sort of inconsistencies? So in particular, what is it about the CMSSM which was making it hard to match the data? And how is it that just relaxing a few of those things suddenly opens up some new opportunities? And so we can start by thinking about what are the main constraints the CMSSM was forcing on us in the first place. The first is the mass. It was kind of putting us in that 10 to 1,000 GeV range. It was making dark matter a Majorana a fermion, and that actually has an effect both on how dark matter scatters and on how it annihilates. It was one of those, the third one is this thing called minimal flavor violation, which is one of those constraints which let us eliminate a lot of those 100 parameters in the MSSM. What that basically said is that any kind of flavor violating processes, which say change first generation quarks, second generation quarks, or something like that, any of those processes which come from new physics have to be proportional to the sources of those processes in standard model physics, which is basically the CKM matrix. Now, making that assumption ends up suppressing a lot of interactions, especially interactions with light quarks, like the stuff which go into protons. And finally, we assume that all the spin-zero superpartners all have universal mass parameters, or mass parameters are all the same, and the same for the spin-1/2 superpartners. And it turns out that changing any of these assumptions has a big effect on the status of WIMP dark matter. And we can kind of break it up into two different things. One is that removing these implicit assumptions allows regions of parameter space, which before we would have said are just excluded from other experiments. But sort of the flip side is that removing these assumptions also allow new signals where we can look for dark matter, where before we would have said, okay, there's nothing to see there, because dark matter models don't predict anything there. It's all because of these assumptions, and we can kind of start seeing signals there when we start removing some of these assumptions. So I kind of want to go through kind of, a little bit what some of these assumptions are and what happens as we remove them. And so one example is looking at this idea of dark matter coupling to protons and neutrons, and this assumption that that coupling is the same. So I've drawn here a figure where, again, I have the mass of the dark matter and the spin-independent scattering cross-section off a proton derived from just a couple of experiments. So I have here a signal region, which amounts to sort of where dark matter could be consistent with the data seen by the Cogent experiment, which is a germanium-based detector. In red here is a similar region for the CMS detector using their silicon detectors. Now this dotted black line is an exclusion curve, also from the CDMS collaboration, but using the germanium-based detector, so the same material as Cogent. And then this is the exclusion bound from the Lux experiment, which uses xenon. Now all these are plotted, looking at the dark matter scattering cross-section against a single proton, rescaling using the assumption that dark matter couples to neutrons and protons in the same way. And so you can look at this and say, well, isn't this all ruled out by Lux? These guys must be seeing some background, because Lux isn't seeing anything. But one way to look at it is to kind of step back and say, well, why would we assume that dark matter couples the same way to protons and neutrons? And in some sense, it's something which is really counterintuitive. It doesn't make a whole lot of sense. And the reason is because the difference between protons and neutrons is essentially the difference between up and down quarks. But WIMPs are things that they're weakly interacting. We expect them to interact with the weak force. And what electroweak symmetry breaking tells us is that the weak force is essentially a mixture of SU2 couplings and a coupling called hypercharge in the standard model. But it turns out that right-handed up and down quarks just have different hypercharge. So if the hypercharge is different, and that's part of the weak force, then why would you expect dark matter to couple the same way to protons and neutrons? And it turns out that that's something which does happen, but very specifically in the CMSSM. And so we can kind of see why that happens. If we imagine the processes by which a dark matter particle could scatter off a quark, there are essentially three different kinds of processes. They can exchange a Higgs boson, they can exchange a Z boson, or they can exchange these squarks, which are the partners of the quarks. And in particular, the up and down, the spin up and spin down quarks, because they're spin 1/2 particles, they have different partners. And you can kind of think of it in terms of handedness. If I have a quark moving in this direction, and I let my fingers curl in the direction of the spin, I have to use either my right hand or my left hand. So that's the handedness of the quark. And each one has a different superpartner, a different squark. And so in the process where I have squark exchange, it turns out my coupling actually is naturally isospin-violating. It couples differently to protons and neutrons because the coupling goes like hypercharge. But it also turns out that spin-independent scattering only occurs if these two different squark states have quantum mixing with each other. Now, of course, they can have quantum mixing. The quantum numbers are the same. There's no reason why they can't have quantum mixing. Except in the CMSSM, if you assume minimal flavor violation, then the mixing for the partners of the first-generation quarks is small. So under that assumption, it happens that the spin-independent scattering is really small, and what you get is spin-dependent scattering. And as we saw, the sensitivity for spin-dependent scattering is actually pretty poor. This kind of diagram I'm making for spin-independent scattering because that's where you can look to see dark matter right now. So that kind of rules out this channel. The second possibility is what if you're exchanging a Z boson. Again, that coupling just goes like hypercharge. So again, that's naturally going to be isospin-violating. But there it turns out if your dark matter is a Majorana fermion and not a Dirac fermion, again, it's only spin-dependent. The spin-independent scattering cross-section cancels. So this one's out the door. And the last possibility is Higgs exchange. And now that one is spin-independent, but it turns out that one happens to be isospin-conserving because a Higgs boson couples to quarks proportional to the quark mass. And because the up and down quark masses are much smaller than the mass of the proton, it means these isospin-violating effects are very small compared to the isospin-conserving effects. So it really turns out that you really needed 3 fairy godmothers in order to make Fn equal to Fp. If any one of them had not been there, then this wouldn't be true. But this all happens to be true in this CMSSM. So this is fine for the CMSSM, but as soon as you move away from that, you can have the possibility of isospin-violating dark matter, which couples different to protons and neutrons. And when you do that, the whole picture changes. So what I tried to do is draw this same picture if I assume that relative coupling is instead minus 0.7. So I get destructive interference between neutron and proton couplings. So what you see in that case is that this region, which before we said was excluded by orders of magnitude, is now actually not even entirely excluded. There are regions of this CDMS silicon data, their preferred region, which are not excluded by the Lux experiment. Now, I'm not trying to say that, well, that means that Fn over Fp is minus 0.7 and here's where dark matter is. I mean, this probably doesn't resolve all the current data. In fact, one thing you'll notice is that I didn't just pick this number out of a hat. I picked this number because this is where you get maximum destructive interference in a nucleus like xenon. So you basically made your xenon bounds as bad as you can possibly make them. And even that doesn't really solve everything, because in doing that, before this agreement between CDMS silicon and Cogent has now gone away. So I'm not so much saying that this resolved the current data. I'm really just saying that whatever data you look at when you look for dark matter, you have to consider this possibility. Looking at a picture like this and saying, well, that means Lux must rule this out, there's really no justification for that, because this is only true in a very specific framework like the CMSSM. And we're already seeing that data makes it hard for the CMSSM to be true. And even before we turned on the LHC, we knew that if the CMSSM is right, dark matter probably isn't sitting at 8 GeV. So if you're analyzing data trying to look for 8 GeV dark matter, it doesn't make a lot of sense to assume it's the CMSSM. So this is kind of one of the ways we kind of broaden how we look at dark matter. I guess I should probably hurry up a bit. Another possibility, for example, is to look at what happens when we go beyond these universal mass parameters. And so, for example, what the LHC tells us, really, is that the partners of the first generation quarks have to be heavy. But it doesn't require the other squarks and leptons to be heavy. Similarly, it tells us that the gluinos have to be heavy. But the other fermions, like the LSP, they don't have to be heavy. And once you break that assumption of universality, what it essentially lets you do is decouple the particles which are really tightly constrained by the LHC from the particles which are useful for getting the WIMP miracle to work. And we can do that just by adding a couple of parameters. And so one simple example is if you, let's say, take the spin 1/2 superpartners. The simplest thing to do is just to make sure that your dark matter is mostly what's called a BINO. So the idea is that all these particles have the same quantum number, so they can all quantum mix with each other. And your lightest particle could be a linear combination of all of those. But the simplest thing to do would be make it dominantly a particle which is the partner of hypercharge. And in that case, dark matter interacts with ordinary matter through exchange of these scalar partners, these spin 0 particles. For the squarks, the simplest thing is actually just to do the same thing we did before, just assume they're all heavy. Because then you explain why the LHC isn't seeing them, and also why you're not seeing any evidence of this from scattering at direct detection experiments. But for the partners of the leptons, the simple thing is now to make them light, and to allow mixing between the spin-up partners and the spin-down partners. And when you do that, you can now satisfy all the LHC bounds from here, but you can now get an annihilation rate which is large enough to get the relic density rate. And that's something I want to briefly spend a slide on, because basically, this is kind of a very generic statement. I just said, if two states quantum mix, suddenly the annihilation rate becomes large. Now, to actually work that out, kind of requires a detailed calculation. But the basics of why that's true is actually kind of a straightforward quantum mechanics exercise. And that's something, which is useful because it not only explains why these deviations from these CMSSM assumptions are useful, but also how it can introduce how it can introduce new signals which we ordinarily don't look for in dark matter. And so the basic way to see how annihilation behaves is just to consider the angular momentum of the process. So imagine we have two dark matter particles annihilating to fermion-antifermion. So something like quark-antiquark or lepton-antilepton. Now, since our dark matter particles are Majorana fermions, our initial state is two identical particles. So we know the wave function has to be antisymmetric. So our initial state is either L equals 0, S equals 0, or L equals 1, S equals 1. Now we can kind of look at what happens with the final states going out. So they're going out back to back, and let's just assume they're going back to back on the z-axis. So we'll put the fermion going out on the z-axis. Now, if the outgoing fermions are on the z-axis, we kind of know right away that the orbital angular momentum projected on the z-axis has to vanish. Now, from the classical point of view, that seems kind of straightforward, just because the level arm is 0, the momentum's all on the z-axis, angular momentum has to go to 0. Kind of the more quantum mechanical way to see it is just to say that if you take your final state wave function and expand the spherical harmonics, this back-to-back process is essentially the process at theta equals 0. And the only way your spherical harmonics don't have a pole at theta, or don't have a node at theta equals 0, is if it's m equals 0. So if it's a spherical harmonic with LZ equals 0. But once you know that, that tells you that the spin projection is equal to the total orbital angular momentum projection. So that means basically you have two possibilities. Either your initial state was this, in which case J equals 0, so JZ equals 0, and your final state is SE equals 0. Or this was your initial state, in which case it was a P-wave state. Now if it's a P-wave state, we know that our annihilation cross-section at freeze-out was suppressed by this v squared, or by a factor of 10. So that makes getting the WIMP miracle hard. And nowadays, we know we're not going to see anything from that, because you have a much larger suppression. On the other hand, now, if this was your possibility, then you're still not out of the woods. So we can look at what that implies for the spin. If the total spin is 0, it means these two fermions have to have opposite spins. So if they have opposite spins, opposite directions, their handedness is the same. So this is a process which produces a fermion and antifermion with the same handedness. The problem is electroweak interactions coupled to fermions and antifermions of opposite handedness. But this was supposed to be a WIMP, so it was supposed to interact through a weak force. So if it's just the weak force, we can't get this final state. In the standard model, there's one interaction which will couple to fermions of opposite handedness. And that's the mass term in the standard model. And what that tells you is it not only determines what are the products you can get from dark matter annihilation, but also what the rates have to look like. So for example, dark matter could annihilate to W plus or W minus, because they're not fermions. So this whole angular momentum argument here doesn't apply. Because the fermion angular momentum, the boson angular momentum will have slightly different constraints. The other possibility is that you could annihilate to things like top quarks or bottom quarks or tau leptons, because those are basically the heaviest fermions. So that means that this mass term which is coupling will be the largest. So that kind of tells you what you're going to annihilate to. But it also tells you that your annihilation cross-section is suppressed by the mass of the fermion over the mass of your dark matter. So if you have something like 70 GeV dark matter, annihilating the tau leptons, that's a huge suppression. And again, you're not going to see anything. So this is part of why this annihilation becomes so hard for these models. But we can also see how we can get around this. So for example, in the CMSSM, that minimal flavor violation assumption basically tells us that everything which should couple to two fermions of opposite handedness all has to go like the mass. But as soon as we remove that assumption, we now get the possibility of other new physics which can do the same thing. And the thing which can do that is kind of what I mentioned here, this mixing of the spin up and spin down partners. Because remember, in the case where the spin is 0, these two things have opposite spins. So one is spin up, one is spin down. They each couple to their partners. And if those partners have quantum states which can mix, now I have some other new physics which allows this process. And that's not suppressed by anything. So suddenly I can ramp up this annihilation rate. Not only that, I can now annihilate to something completely different from what we were talking about here. So for example, I can now annihilate to neutrinos and antineutrinos. Okay, before I would say that's extremely small because these things are massless. But now I can have a completely unsuppressed annihilation rate to that. And that can give you, you can imagine maybe you can get a very distinctive signal out of neutrino detector. You're getting monoenergetic neutrinos from dark matter annihilation. Another thing you can get are, for example, E plus E minus pairs or me plus me minus pairs. And that can give you some very nice signals like cosmic ray detectors. So I'm going much more slowly than I had hoped. I think I'll have time to get through this and then I'll wrap up. So kind of the last thing we can kind of think about is sort of what happens if we try to go beyond this idea of the WIMP miracle. And in particular, try to think about what was really fixing this ratio g to the 4th over m squared, which is kind of setting our annihilation cross-section. Kind of how that works in the framework of our original CMSSM. And kind of the basic way to think about it is that in our MSSM WIMP paradigm, basically you have a bunch of standard model particles which are effectively massless, which are really light. You have the photons, the electrons, even the protons and neutrons. They're all relatively light compared to where we think dark matter is. Now, if supersymmetry were unbroken, all the superpartners would have the same mass. They basically have all the same quantum numbers. But we expect all those particles to be heavy because of supersymmetry breaking. So all those superparticles sit at a mass scale, which is essentially set by an energy scale, the supersymmetry breaking scale. Not only that, we expect a bunch of other particles to be there. That's what we expect the W bosons to be at, the Z bosons to be at, the Higgs boson. Basically, you kind of think about it as that's the next ruler in your problem. That's the next notch on your rule. If you try to calculate what would the mass of these particles be, essentially that's the next energy scale which could appear in your calculation. And that kind of is deeply ingrained in how people use supersymmetry to explain the hierarchy problem, why these masses are where they are and not at something like the Planck scale. And so then all you need is some new symmetry, and particularly in this case it's R symmetry, which stabilizes the particle which happens to be at this SUSY breaking scale, which because of this is now tied to the weak scale. And so that's how you get a WIMP. If I draw this line here, which is essentially a line of constant g to the 4th over m squared at a picobarn, you needed a coupling which was a weak coupling, a mass which is a SUSY breaking mass. And then you need the miracle, which is that line happens to be on this 1 picobarn line. But now we can ask, what if we had dark matter instead in something like a hidden sector? And by a hidden sector, all I mean is a new set of particles which don't interact with standard model forces, but have their own forces which they interact with, but which standard model particles don't interact with. Now, if that's the case, again, we'll have the same kind of scenario. We'll have a bunch of light particles there, but then there's some supersymmetry breaking, and that becomes kind of the next notch on the ruler. So there are a bunch of particles whose mass involves that scale, and so their masses are all sitting in about that energy scale. And then we'd want to ask for some kind of a symmetry which stabilizes a particle which happens to be at the supersymmetry breaking scale of the hidden sector, which again could be anything. We don't know what it is. But the nice thing is that in a lot of the well-studied models of supersymmetry, the supersymmetry breaking scale is proportional to the coupling of the forces. And so what that means is that you're kind of automatically, your hidden sector is automatically forced to be on this line of constant g to the 4th over m squared. And the fact that, the weak scale happens to be on the line at 1 picobarn tells us every hidden sector has to be on the same line. So our dark matter mass could be anything. But you automatically know the relative density is going to be right. It could be much less than this 10 GeV, much greater than 1,000 GeV. Right, in this kind of scenario, your relative density is automatically exactly right. Or not exactly right, approximately right. So it kind of gets, your relative density right even when you're outside that standard WIMP mass range. And so maybe I'll just try to end here just by saying that, kind of looking forward, a few points worth considering are just that, different direct detection experiments, we've already seen that, they have different sort of sweet spots where, their sensitivity is peaked as a function of their mass. Moreover, we need at least 2 direct detection experiments with 2 different target materials, and probably more, if we want to identify what's the relative coupling between protons and neutrons, and which experiments are more sensitive than others. So in that case, right now we're at a point where a lot of people in the community are trying to decide what should be the next generation experiments to build. And kind of the lingo people always use is we need to identify what's the best technology. But it's worth considering that, there really isn't any one best technology yet. Until you know really what you're looking for, you don't know what's the best way to look for it. Now, we started out with essentially the simplest dark matter framework, and largely we've interpreted data in light of this framework. And in many ways, this was clearly the right thing to do when you were just building direct detection experiments and trying to see if you understood what you were doing, what you were looking for. But now that we're getting a lot of data, maybe the only thing we're really seeing is that this framework might be too simple. And as we go past this framework, what we're finding is that not only are there many new places to look for signals, but there are also many new models which can match data. And our focus, as we go forward, for example, could be on understanding things like how the relative coupling between protons and neutrons comes into play. How, for example, if your scattering depends on the velocity of particles, how that changes the way we look at data. Annihilation to new channels like, lepton channels or neutrinos. What happens if the mass is outside this range, which we've been preferring with our dark matter experiments and with our models, and how all our assumptions play into how we correlate data from direct and indirect detection experiments with the Large Hadron Collider. And so I think I kind of went a bit over time, so let me just skip the part about new detectors, except to say that Lux and Ku are coming out with new data soon, and just put up my conclusion slide. Thank you.
So is there any guidance from string theory that would tell you that CMSSM is preferred over other kinds of?
Well, I don't think there will be any guidance from string theory on that. And if anything, I think string theory will probably tell you the opposite. But I think, I would say that I don't think string theory really would push towards the CMSSM in any way. Not that I can think of, at least.
Is there any I don't know, if you can explain to me, as a simple person, how P-wave annihilation suppresses radiation?
Oh, you mean why P-wave annihilation is suppressed?
Yeah.
So one way to look at it is that if you're annihilating from a P-wave state, then it has to depend on the fact that you have angular momentum. So in the limit where your momentum goes away, then your annihilation cross-section will go to 0. And that kind of tells you that the matrix element has to be proportional to the velocity of the particles. Because as you make that go to 0, you make the angular momentum go to 0, then your annihilation cross-section goes away. So you know your annihilation matrix element has to be proportional to the velocity, and that means that the cross-section has to be proportional to velocity squared. But then in the non-relativistic limit, that's going to give you a suppression. Does that answer your question?
Well, I'd like to have a picture of what this P wave looks like. What is the P wave that?
Oh, okay, so one way to look at it, maybe if you kind of drew it like this, is...
WIMPs that are approaching each other but not head-on, or what?
Yeah, so the idea is that you could imagine that you had some particles approaching each other. And there's some interaction. So I guess let me... And they exchange some intermediate particle at some distance from each other. And it turns out if you compute the matrix element, sometimes you'll find that this will depend on velocity, which basically means that if I try to decompose this process into all the possible angular momentum states, make it a sum of those, it only depends on one where they have some relative velocity and there's some angular momentum for them. Essentially, in the limit where the impact parameter becomes really small, if you think of it from a classical point of view,
Well,
then,
that's what I was looking for.
yeah, maybe in the limit where the impact parameter becomes very small, then you don't get anything.
Okay,
Yeah.
that's weird.
Mm-hmm. Well, P-wave annihilation is kind of weird. So.
So, I got linked to a study a couple days ago that was talking about some observations of a 3.5, I think, GeV line?
KD.
KD line?
Mhm.
That they thought was this thing they called a sterile neutrino.
Yeah.
So I was wondering
If that could be related to dark matter?
yeah.
It certainly could be related to dark matter if that kind of holds out. So I'm not yet sure, if what the statistical significance of that is. But it's certainly something people are looking at in the context of dark matter in terms of can you have dark matter models where either dark matter decays with a very low decay rate, so a very long lifetime, or dark matter annihilates in some way and you produce photons of this type. So people have been thinking about it in that line.
All right, I think we better thank Jason again. And if you're interested in going to dinner, please come and see me so we can make a final plan. Okay, Jason, we did take you.